training robots directly in the real world is slow, risky, and expensive. A legged robot that falls thousands of times while learning to walk wears hardware and endangers nearby equipment. An autonomous vehicle cannot explore dangerous edge cases on public roads. Warehouse trials block aisles and burn labor hours. Simulation and digital twins exist so agents learn, fail, and iterate at digital speed before touching production metal or public space. Simulation shifts learning curves from weeks of hardware time to hours of compute. Simulation offers 3 superpowers. Scale, run millions of episodes overnight with parallel workers. Safety, explore collisions, drops, and near misses without injury or downtime. Repeatability, replay the exact scenario that caused a failure and test fixes deterministically. These advantages accelerate research and product development when paired with disciplined validation on real hardware. Simulation is not a replacement for reality. It is the fast front end of a sim-to-real pipeline. Automated regression turns yesterday's failure into tomorrow's required pass case. Physics engines integrate forces over time, resolve contacts, and enforce joint limits. Accuracy trades off against speed. Some engines target interactive rates for reinforcement learning. Others target high-fidelity multibody dynamics for control research. Choosing an engine means matching its contact models, solver stability, and sensor simulation to your robot class. A quadcopter trainer cares about aerodynamics. A grasping trainer cares about friction and compliant contacts. Differentiable simulators increasingly support gradient-based system identification. Mu-Jo-Co excels at fast, stable contact-rich simulation for locomotion and manipulation research. NVIDIA ISIC sim couples GPU rendering, synthetic data, and robot assets for large-scale perception training. Gazebo has long served ROS ecosystems with modular plugins, powers many game-style simulators with efficient collision. Drake from Toyota Research emphasizes rigorous multibody dynamics and optimization-friendly models. Teams often use more than one engine across project phases. Asset pipelines, meshes, ERDFs, and material tags often bottleneck projects more than solver choice. A digital twin is not an offline toy model. It is a living simulation tied to a real machine, line, or building through telemetry. Factory twins track robot health, throughput, and bottlenecks. Vehicle twins replay sensor logs to test software updates before over-the-air deploy. When sync is tight, operators ask what-if questions on the twin, swap a gripper, add a worker, change a layout, and see predicted effects before changing physical production. Twins also support training operators before new lines go live. Simulation generates labeled images, depth, segmentation, and LiDAR with perfect ground truth. Rare events, pedestrians at night, defective parts, spilled liquids, appear on demand. Domain randomization varies backgrounds, materials, and camera placement so models generalize. Synthetic data augments real datasets. It rarely replaces them entirely. The art is mixing sim and real so detectors survive the textures and noise of deployment cameras. Real-to-sim alignment tools match lighting and lens distortion from deployment cameras. Domain randomization perturbs simulation parameters: mass, friction, motor delay, lighting, and sensor noise. The policy learns invariance instead of memorizing one perfect scene. Randomize too little and transfer fails. Randomize too much and learning becomes impossible. Curriculum strategies start easy and widen variation as competence grows. Randomization is the bridge between crisp simulation math and the stubborn variability of physical hardware. System identification narrows randomization ranges once real hardware telemetry arrives. No simulator captures every effect. Cable stretch, thermal drift, floor imperfections, and human unpredictability live outside the model. Policies overfit to sim visuals or exploit physics bugs. Controllers tuned in ideal contact bounce on real rubber. Closing the gap combines randomization, system identification on hardware, sim fine-tuning from real logs, and conservative safety envelopes at deploy. Expect a gap. Engineer processes to shrink it continuously. Human behavior remains notoriously hard to simulate credibly for HRC scenarios. Simulation wins on volume, automation, and dangerous scenarios. Reality wins on fidelity, human interaction, and certification evidence. Production teams treat sim as the first gate and hardware as the truth oracle. A policy that never meets real contact forces is untested. A policy trained only on hardware is underexplored. The winning workflow loops both directions. Sim pre-train, real evaluate, log failures back into sim assets. Certification bodies still demand physical test evidence for safety-critical releases. Reinforcement learning fits simulation naturally. Define a reward, reset the scene after failure, and parallelize thousands of environments. Locomotion, grasping, and navigation policies emerge from trial and error. Sim provides cheap resets. Real robots cannot afford 10,000 falls per hour. Reward design still matters. Misspecified rewards produce jumping, vibrating, or grasp-cheating behaviors that look successful in sim and absurd on hardware. Off-policy algorithms reuse old trajectories, improving sample efficiency inside sim farms. Hardware in the loop runs real embedded software against simulated physics in real time. Test firmware before it spins motors on a prototype. Inject sensor faults and network delays safely. Automotive and aerospace rely on this discipline. Robotics adopts it as arms and mobile bases become software-defined. The boundary between sim and real blurs when the same control binary toggles between virtual and physical plants with identical interfaces. Identical APIs let the same binary run against sim or hardware with a compile flag. Factory digital twins simulate conveyor speeds, robot reach, and human walking paths before capital equipment is ordered. Warehouse twins test slotting strategies and peak season congestion. Fleet simulators validate multi-robot routing under aisle closures. These models save millions when they catch a layout choke point on screen instead of after install. Twins stay valuable post-launch as live KPIs recalibrate predictions. Energy and maintenance models extend twins beyond pure throughput questions. AV stacks log billions of simulated miles, jaywalking pedestrians, cut-ins, construction zones, and weather. Scenario libraries replay regulatory test cases and internal near misses. Sensor simulation stress tests fusion under dropped frames. Software releases pass sim regression gates before track days. Simulation cannot certify every real-world nuance, but it compresses discovery of catastrophic bugs into hours instead of years of driving. Scenario fuzzing mutates parameters around near-miss logs to hunt unknown unknowns. Teams must report sim metrics and real metrics side by side. Track success on held-out real objects, not only training sim scenes. Measure sim exploit rate when physics parameters shift. Log which failure modes sim never reproduced. Digital twins need freshness checks. When the physical line changes and the twin does not, decisions drift wrong. Honest validation keeps simulation a trustworthy accelerator instead of a vanity leaderboard. Version sim assets alongside code so old policies remain reproducible. Start with accurate robot and environment assets. Train policies or perception models with randomization. Run hardware identification to match inertias and delays. Deploy behind safety limits with logging enabled. Feed real failures back into sim scenarios within days, not quarters. Assign owners for sim assets like any production dependency. When this loop runs tight, iteration speed becomes a competitive advantage instead of a research luxury. Executive dashboards should show real KPI movement, not sim leaderboard scores alone. Simulation makes robot learning scalable and safe. Physics engines from Mu-Jo-Co to Isaac Sim, Gazebo, and Drake trade fidelity for speed across tasks. Digital twins sync with live systems for what-if planning and monitoring. Domain randomization and disciplined validation attack the sim-to-real gap. Factories, warehouses, and AV programs depend on these tools to explore failure before it reaches customers. Train in software, prove on hardware, and keep the loop running. Treat simulation as infrastructure with owners, SLAs, and freshness checks, not a side project.